Welcome to Module 4 of this training course on the Internet of Things for hydrologic measurements. My name is Douglas Nyole. This module is part of a series of modules that have been prepared for this training. In this module, we will aim to better understand the IoT processing unit or the IoT microcontroller. Therefore, this module covers the theory and the hands-on skills by interacting with an IoT processing unit. If you recall, in Module 2, we discussed the four main components of an IoT. That is the device or sensor, the platform, the communication, and the application. Under platform, we mentioned that the platform may be hosted in a local computing or processing unit in the form of a hardware, acting as a microcomputer or microcontroller. That is what we will be using in this IoT training. In Module 2, we also gave examples of local processing units currently available in stores or markets, such as products from Arduino, Picom, Adafruit, and Raspberry Pi. In this training, we will be using a microcontroller or processing unit from Picom, which you will get to start using later in this module. We invite you to visit the Picom website to know more about what products and learning materials they have for building your own IoT project. Why have we chosen the Picom microcontrollers? Simply because Picom microcontrollers are programmed using Python programming language through its light version called MicroPython. But why have we also chosen Python programming language? Python is a popular, high-level, and easy-to-learn programming language because it has simplified syntax that try to mimic the natural human-to-human language that we use. To create the IoT platform on an IoT processing unit, we start by creating the instructions in the form of a MicroPython script. The scripts are written using a regular PC or laptop. We then connect the microcontroller to the computer using a cable, such as a micro USB cable, after which we upload the scripts to the microcontroller and start running the scripts. We program the scripts to ensure that they continue running even after we disconnect the microcontroller from the computer, provided the microcontroller is powered using different sources of power, which we will discuss later. Remember, Python scripts are executed in a computer, while MicroPython scripts are executed in a microcontroller. The IoT processing unit is made up of a number of components. These are the development board, or what we commonly call the module, an expansion board, accessories, scripts or software, and the network. The first three are in the form of hardware, while the rest are not. Let's now go ahead and look at each of the components. The first component that we'll explain is a development board, which is commonly referred to as a module. This is a hardware in the form of a printed circuit board that carries the microprocessor and other important items required in an IoT, which we'll explain and show in the next slide. Therefore, think of the development board as being the host of the IoT processor. The development board is this upper part of the IoT processing unit. So, what is contained in a development board? In this image, we will show you some of the key IoT items that a development board contains, which are used when building an IoT system. The first item we will show is a microprocessor, which is at the point indicated in this image, though hidden. The LoRa or Sigfox transmitter is also hidden at the center of the development board, together with an 8 MB flash memory. Depending on the network you choose to use, the network antenna may be connected to the development board using one of the connection points at the three corners indicated above. And if you choose to use Wi-Fi, then an antenna is already installed at the top right corner of this development board. We also have a reset button or switch to reset the development board and an LED light to respond to different instructions and give an indication. We also have other switches such as a noise switching regulator and RF switch. In this slide, we will have a quick look at some of the development boards provided by PyCom. The first development board is the YPy. We also have the SciPy development board, the LoPi4, the GPy, and the PhiPy. Take some time to have a closer look at each of the development boards. Can you figure out the difference between these boards? Do the differences you make have any links with their respective names? Note your answer somewhere, because later we will discuss this when we will be covering a specific component of the IoT microcontroller. The next component of the microcontroller that we will discuss is the expansion board. We are all familiar with what a motherboard is. According to Wikipedia, we can say a motherboard, also called mainboard or main circuit board, system board, baseboard, planner board, logic board, or mobile, is a main printed circuit or PCB in general purpose computers and other expandable systems. It holds and allows communication between many of the crucial electronic components of a system, such as the central processing unit and memory, and provide connectors for other peripherals. What we see here is an example of a regular PC or laptop motherboard. Similarly, an IoT has a motherboard, referred to as the expansion board. The expansion board is therefore a printed circuit board that is connected to a development board to give it added functionalities such as communication between essential components of the IoT system. Therefore, from this image of a microcontroller, we have the development board and the expansion board that are always connected to each other, at least for the PyCom products. And what is a PyCom board composed of? A PyCom expansion board comes with connection pins numbered from P0 to P23 as clearly indicated in the board. Other boards have them numbered from G1 to G23, so be careful not to confuse them, especially when you change the boards and need to adapt your scripts to the new board. The expansion board also has pins for power supply, GND or ground, serial, control, port, and analog. We also have a micro USB connection port, a JST for LiPo battery, USB to serial converter, charge indicator LED, user LED connected to P9, user push button, user save button, and micro SD card reader. When connecting the development board, ensure that it is connected to the expansion board as indicated in the image, that is with the RGB LED positioned with the micro USB port. We will demonstrate this during the hands-on training. In this slide, we see an expansion board with the pins indicated from G1 to G23, as I had earlier mentioned in the previous slide. The third component of the processing unit are the accessories. These are the other items required with the processing unit to ensure that we have an optimally functioning processing unit. The first item, which is very essential for a processing unit, is antenna together with its cable. These enable the microcontroller to transmit data using the selected communication option, for example LoRa or LTE. We may also require a GPS, that's if we need to track the location of the microcontroller. To protect our microcontroller, we need a casing like the one we see here. We also need a micro USB cable to connect directly to the microcontroller. A source of power for the microcontroller is also necessary, which can be obtained from a LiPo battery like the one we see here, especially for outdoor IoT systems. The fourth component required by a processing unit are the software. These are the applications that are designed to be used to either code for, communicate with, and manage the modules. Some examples of these softwares that are provided by PyCom specifically for its development boards are PyMaker, PyBite, PyMesh, and PyLite. Now let's spend some time to distinguish each of these softwares and or applications. Let's start with PyMaker. PyMaker is an application created in the form of a plugin. It is at present created to be plugged into Atom and Visual Studio Code, which are some of the popular code editors. Using PyMaker installed in one of these code editors, one can develop scripts using MicroPython, which are then later uploaded into the microcontroller or processing unit for testing before running the IoT system using the final scripts or instructions. To install PyMaker into your code editor, you simply search for it from the available packages and click install, as you can see in this image. Later on, we will demonstrate how to do this. The next application provided by PyCom is PyBite. This application was developed to support with device management and is available for all development boards and modules from the PyCom family. With this application, you can therefore add a device, configure networks, create a project, maintain a device, and many more operations. The application is provided as a software that is installed into your PC or laptop, or as a mobile application. The next application is PyLife, which is digital dashboard or platform for PyCom devices that enables owners to share their devices with others. Finally, we have PyMesh, which offers a PyCom product user with a flexible long-range or LoRa mesh network to be able to create your own personalized LoRa network. The fifth and final component of a processing unit is a network. PyCom produces different development boards that allow a user to choose from based on the network preferred. That's to say that the choice of network to use for your IoT project should inform you on the right PyCom module or development board to procure. These 5 network options are Wi-Fi, Bluetooth, LoRa, Sigfox, or LTE. Earlier in this presentation, I showed you these images and left you to try and spot the differences between these development boards. And I gave you a hint of trying to link the noted differences with their respective names. Well, the answer lies on the network options available for these different development boards. All these development boards can use Bluetooth, as you can see indicated in each of them. In the first one, they only added Wi-Fi, and probably that is why they named it Wi-Fi. The second board has Bluetooth, Wi-Fi, and Sigfox. Probably that's why they call it SciPy, because they introduced Sigfox. The third one has Bluetooth, Wi-Fi, Sigfox, and LoRa network capabilities, and is called LoP4, probably because they introduced LoRa to it. The number 4 may have been added because it can transmit using 4 network options. The fourth board has Bluetooth, Wi-Fi, and LTE. This board lacks Sigfox and LoRa. I don't know why they left this out. So the board is called GPy, probably because LTE or the 4th generation 4G network option was introduced to it. You are all familiar with 4G or LTE networks in your mobile phones. The fifth and final board has all the 5 network options available for PyCom development boards. That is Bluetooth, Wi-Fi, Sigfox, LoRa, and LTE. Probably that's why they called it 5Pi, for 5 and Pi. For this course, we will be using LoRa network. So these 2 boards are relevant to this training course. A PyCom board, specifically LoP4, can be programmed to serve as a gateway. Therefore, one LoP4 may be configured to connect and manage the sensors, while a separate LoP4 board also is configured to receive data through LoRa network from the first LoP4 board, then use Wi-Fi with internet to transmit data to a server. In this image, we see an example of a LoP4 being used as a gateway, and that is what we will do later in this course. So what happens in a complete IoT setup that uses LoRa network through a LoPi board is that one LoPi board is set up and sensors connected to it. It then transmits data using LoRa network to a LoPi gateway. The LoPi gateway then connects to the internet using Wi-Fi and sends the data to the cloud services, for example, to the Things network, which are then sent using different network protocols to a server platform of your choice, for example, a proprietary platform like ThingsSpeak or a personal platform. From here, the data is processed for quality control and can also be stored, visualized, or downloaded. From here, we will now start with a basic hands-on exercise. This will cover the basic interactions with an IoT processing unit made up of the development board and the expansion board connected to a computer using a micro USB cable. In readiness for this hands-on exercise, ensure that you have downloaded and installed Visual Studio Code into your laptop from the website link provided below. Next, you also need to download and install Node.js from the link provided below. This creates a JavaScript runtime environment required by PyMaker plugin, which we will demonstrate on how to install in the next slide. Also ensure that you have a microcontroller, which is the development board and expansion board, as you can see in the bottom right image. Finally, ensure that you have a USB-A to micro USB cable like the one below. In this section, we will demonstrate how to install the PyMaker. So go ahead and launch the Visual Studio Code. Click on the extension as indicated. In the search section, type PyMaker to be able to search for it. And immediately PyMaker will be displayed. Click on PyMaker plugin. It will give you the option to install. Go ahead and click on install to install the PyMaker plugin. This should take a few minutes and you'll be done. Now that we've installed Visual Studio Code into our PC and we've installed PyMaker plugin into Visual Studio Code, we'll go ahead and connect the microcontroller to our PC. And to do this, we need a cable, that is a USB-A to micro USB cable. So go ahead and connect the microcontroller to your PC. Once you've connected your microcontroller to the PC, ensure that the LED on the module has a blue flashing light. Also ensure that the USB power on has a green or yellow light. And finally, ensure that the LED power on has an orange light. Now that we have connected the microcontroller to our PC, and in this case the LoPi 4, we will go ahead and start the terminal. So go ahead and start Visual Studio Code. The terminal should be ready if PyMaker console identifies the right COM port, as you can see here. So it should be able to write that you're connected to the COM 9, in this case for my connection. However, if it didn't connect to the right COM port, it will indicate that it failed to connect. So we need to fix this. If the PyMaker console failed to identify the right COM port, then we will start with the basics of trying to fix the issue. The first step would be trying to reconnect the Pico microcontroller and reconnecting the PyMaker. To do this, we simply disconnect the microcontroller from the PC and reconnect it again. Start the terminal once again, and using the PyMaker console, try to reconnect PyMaker. You may also try to reset by pressing the reset button to the left of the LED to restart the terminal, as indicated here. After repeating that procedure and you still can't connect, then it's possible that the microcontroller is connected to one COM port, while the PyMaker is trying to read from another. So this needs to be fixed. And to be able to know if they're reading from different COM ports, you simply go to the device manager and then click the drop-down menu as indicated to be able to see. And from here we can see that the microcontroller is connected to COM 10, while the console was trying to connect to COM 9 as indicated here. To correct this COM port issue, we will need to edit the PyMaker project settings to the right COM port that the computer is using to connect to the microcontroller. And to do this, we will go ahead and click on all commands. In the drop-down list, select the project settings. Then go ahead and edit the address to the right COM. So edit COM number to match the device manager and save it. Now check that the PyMaker can successfully connect to the microcontroller. And to do this, we'll once again go to the all commands. In the drop-down list, select connect. And now we are connected to COM10 and not COM9. So we're ready to move to the next step. Up to this level, we've been able to connect the microcontroller to the PC. And the terminal, that is the Visual Studio Code together with PyMaker, are able to communicate and connect with the microcontroller. So next we will try and communicate with the microcontroller and give it instructions. And the first of that we are going to do would be to run the RGB colors in LED. So by this level, you have downloaded the file PyCom Basics and saved it in your PC. You may have downloaded it from our GitHub account, or you may have received it from a different source. But what's important is that you have the PyCom folder saved into your PC. Now, using the file, open the file in Visual Studio Code and navigate to the folder PyCom Basics where you have saved it. And then select and open the file rgb.py. Once you've opened the file, that is rgb.py, go ahead and upload it as indicated below. Once you've uploaded this file, you should be able to start running it. So go ahead and click on the run to run the script. Does the LED change its color? If you followed all the instructions correctly, then by now your microcontroller should be blinking red, green, and blue in the LED light. To be able to know that your script is still running, then the terminal should appear like this, as indicated in the red cycle. However, once the script stops running, the terminal should be as indicated below. Kindly note the difference between the two. If you want to stop a script that is still running, all you need to do is to press the Ctrl and C commands. This will stop the terminal and the script will stop running. Remember, to stop a script that is running, you need to select the Command plus C button. So go ahead and press the Command plus C button to stop the rgb.py file that is still running. Once you've done that successfully, now still under the folder basics, select alarm.py file and upload it. Once you've uploaded it, go ahead and run this script. What do you see, or what do you observe? After how long does the alarm stop counting? Take note of that. Now go ahead and edit the script. And to do this, we need to change the script and make the alarm to stop counting after 20 seconds. Remember to stop running the script using the Command C button. After editing this file, go ahead and save the script, upload it, and run it again. What do you notice? If you followed all the instructions correctly, then we've interacted with the microcontroller correctly, and that's the end of this presentation.